Before we explore 8 recently discovered exoplanets, if you enjoy calm, factual journeys like this, please consider liking and subscribing. It helps support the channel. Gliese 12b is one of the most recent and intriguing exoplanets discovered near our solar system, located approximately 40 light-years away from Earth in the constellation Pisces. In astronomical terms, this places it relatively close, making it an important target for future observation and study. The planet orbits a red dwarf star, a type of star that is smaller, cooler, and far less luminous than our Sun. Red dwarfs are the most common type of star in the Milky Way galaxy, and many of the exoplanets discovered in recent years have been found orbiting them. Because these stars emit less energy, their habitable zones, the regions where liquid water could potentially exist, are much closer in than in systems like our own. Gliese 12b completes a full orbit around its star in just over 12 Earth days. This short orbital period means the planet is significantly closer to its star than Earth is to the Sun. Despite this proximity, the lower energy output of the red dwarf means the planet may not be as extremely hot as one might expect. Current estimates suggest that its surface temperature could fall into a range that is comparable to, or slightly warmer than, Earth's. Although this depends heavily on one key factor: its atmosphere. In terms of size, Gliese 12b is remarkably similar to Earth. It is classified as a terrestrial or rocky planet, rather than a gas giant like Jupiter or Saturn. This makes it particularly interesting to scientists, as Earth-sized rocky planets are considered some of the most promising candidates when searching for potentially habitable environments beyond our solar system. However, one of the biggest uncertainties surrounding Gliese 12b is whether it has an atmosphere at all. Early observations suggest that it may lack a thick atmosphere, which would have significant implications for its ability to support stable temperatures or protect its surface from stellar radiation. Without an atmosphere, the planet would experience extreme conditions, with heat from its star directly impacting the surface and rapidly escaping back into space. The discovery of Gliese 12b was made using the transit method, one of the most effective techniques for detecting exoplanets. This method involves observing the slight dimming of a star's light as a planet passes in front of it. By carefully measuring these dips in brightness, astronomers can determine the planet's size, orbital period, and distance from its star. What makes Gliese 12b particularly valuable is not just its size or location, but its potential for further study. Because it is relatively close to Earth and orbits a dim star, it provides an opportunity for advanced telescopes, such as the James Webb Space Telescope, to analyze its atmosphere, if one exists, in greater detail. Scientists hope to detect gases such as carbon dioxide, water vapor, or other molecules that could provide clues about the planet's composition and history. At present, Gliese 12b sits in a category of planets that are often referred to as Earth analog candidates. These are worlds that share some characteristics with Earth, but remain fundamentally unknown. It may be a dry, barren landscape with no atmosphere, or it could retain enough gases to create a stable climate. The difference between these possibilities is critical, and it is something astronomers are actively working to understand. The study of planets like Gliese 12b is part of a broader effort to answer one of the most fundamental questions in science. How common are Earth-like worlds in the universe? Each new discovery adds to a growing data set that is helping scientists refine their models of planetary formation, atmospheric evolution, and the conditions required for habitability. Gliese 12b does not provide all the answers, but it represents an important step forward. It is close enough to study, similar enough to Earth to be relevant, and different enough to challenge our understanding of what makes a planet truly habitable. As more observations are conducted in the coming years, this distant world may reveal further details about its surface, its atmosphere, and its potential to resemble environments we recognize. Until then, it remains a quiet, distant planet orbiting a dim red star, one small part of a vast and still largely unexplored universe. TOI 715b is a recently identified exoplanet located approximately 137 light-years away from Earth. It orbits a small red dwarf star, placing it within a growing group of planets that are considered especially important in the search for potentially habitable environments beyond our solar system. The planet is classified as a super-Earth, meaning it is larger than Earth, but still rocky in composition. Current estimates suggest that TOI 715b is about 1.5 times the size of our planet. This size difference may seem small, but it can significantly affect the planet's gravity, atmosphere, and overall surface conditions. What makes TOI 715b particularly notable is its position within the habitable zone of its star. The habitable zone is the region where temperatures may allow liquid water to exist on a planet's surface, assuming the presence of a suitable atmosphere. Because the host star is a red dwarf, this zone lies much closer to the star than it does in our own solar system. TOI 715b completes an orbit around its star in a relatively short period, likely on the order of a few weeks. Despite this close orbit, the lower luminosity of the red dwarf means the planet does not necessarily experience extreme heat. Instead, it may receive an amount of stellar energy comparable to what Earth receives from the Sun, making it a candidate for further study. However, being located in the habitable zone does not guarantee that the planet is habitable. One of the most important unknowns is the nature of its atmosphere. A thick atmosphere could trap heat and create stable surface conditions, while a thin or non-existent atmosphere would leave the planet exposed to temperature extremes and stellar radiation. Planets orbiting red dwarf stars also face additional challenges. These stars are known for stellar activity, including flares that can emit bursts of radiation. Over time, this activity can strip away a planet's atmosphere, especially if the planet lacks a strong magnetic field. Whether TOI 715b has retained its atmosphere under these conditions remains an open question. The planet was detected using the transit method, where astronomers observe periodic dips in a star's brightness as a planet passes in front of it. From these observations, scientists can determine the planet's size, orbital period, and distance from its star. Follow-up measurements may also provide insights into its mass and density, helping confirm whether it is truly a rocky world. One of the reasons TOI 715b has attracted attention is the possibility that it may be part of a larger planetary system. Early observations suggest there could be additional planets orbiting the same star, potentially including smaller, Earth-sized worlds. If confirmed, this would make the system an even more valuable target for future observation. Because of its relatively close distance to Earth and its location in the habitable zone, TOI 715b is considered a strong candidate for atmospheric study using next-generation telescopes. Instruments like the James Webb Space Telescope are capable of analyzing the light that passes through a planet's atmosphere during a transit, allowing scientists to search for gases such as water vapor, carbon dioxide, or methane. These observations are not just about identifying individual planets, but about building a broader understanding of how planetary systems form and evolve. Each new discovery helps refine our models and improves our ability to identify worlds that may share characteristics with Earth. TOI 715b represents a balance between familiarity and uncertainty. It is larger than Earth, closer to its star, and subject to conditions that may differ significantly from those on our own planet. At the same time, its position in the habitable zone and its rocky composition make it one of the more compelling targets in the ongoing search for potentially life-supporting environments. For now, it remains a distant world, orbiting quietly around a dim red star. Its true nature, whether it is a warm, stable planet or a harsh and inhospitable environment, is still unknown. But with each new observation, we move closer to understanding not just this planet, but the broader diversity of worlds that exist throughout the galaxy. K218b is one of the most closely studied exoplanets in recent years. Located approximately 120 light-years from Earth in the constellation Leo, it orbits a red dwarf star and has attracted significant attention due to evidence suggesting the presence of water and a potentially complex atmosphere. The planet is significantly larger than Earth, with a radius about 2.6 times greater and a mass roughly 8 times higher. This places it in a category between Earth and Neptune, often referred to as a sub-Neptune. Unlike smaller rocky planets, worlds of this size are expected to retain thick atmospheres composed primarily of lighter gases. K2-18b orbits within the habitable zone of its star, meaning it receives a level of stellar radiation that could allow liquid water to exist under the right conditions. However, its structure is likely very different from Earth's. Rather than having a solid surface with oceans on top, scientists believe K218b may be what is known as a Hycean planet. Hycean planets are theorized to have deep, global oceans beneath a dense, hydrogen-rich atmosphere. In this scenario, the surface is not exposed land, but an immense ocean that could extend for hundreds of kilometers. Above it, a thick atmosphere would trap heat and create high-pressure conditions, very different from anything found on Earth. What makes K218b particularly important is the detection of molecules in its atmosphere. Observations using the James Webb Space Telescope have identified the presence of carbon dioxide and methane. These gases are of interest because, on Earth, they are often associated with biological processes. However, they can also be produced through non-biological mechanisms, so their presence alone does not indicate life. There has also been tentative evidence suggesting the possible presence of dimethyl sulfide, a molecule that on Earth is produced primarily by marine organisms. This detection remains uncertain and is still being studied, but it highlights the potential of K218b as a target for future atmospheric analysis. The planet was initially discovered using the transit method, where periodic dips in the brightness of its host star revealed its presence. Over time, repeated observations have allowed scientists to refine measurements of its size, orbit, and atmospheric composition. One of the key challenges in understanding K218b is determining the true nature of its atmosphere and internal structure. While it may host a global ocean, the pressure and temperature conditions could be extreme. The hydrogen-rich atmosphere would likely create a strong greenhouse effect, potentially leading to temperatures that are too high for life as we know it. In addition, the depth of the ocean and the lack of a solid surface could limit the types of chemical interactions that are thought to be important for the development of life. These uncertainties make K218b both intriguing and difficult to interpret. Despite these challenges, K218b represents one of the best opportunities to study a potentially water-rich world beyond our solar system. Its relatively close distance and the characteristics of its host star make it an ideal candidate for detailed atmospheric analysis using current and future telescopes. The study of K218b is part of a broader effort to expand our understanding of planetary diversity. It challenges the traditional view that habitable worlds must closely resemble Earth and suggests that there may be entirely different types of environments where life could potentially exist. For now, K218b remains a distant and complex world, one that sits between categories, neither fully Earth-like nor entirely alien in a way we can easily define. Its atmosphere, its possible ocean, and the chemical signals detected within it continue to make it one of the most compelling exoplanets discovered to date. As observations continue, it may provide clearer answers about the nature of Hycean planets and the range of conditions under which life might arise. Until then, It remains a key piece in the ongoing exploration of worlds beyond our own. WASP-193b is one of the most unusual exoplanets discovered in recent years, located approximately 1,200 light-years away from Earth. It orbits a star similar to our Sun, but what makes this planet remarkable is not its distance or its orbit, it is its density. The planet is extremely large, comparable in size to Jupiter, yet its mass is extraordinarily low. This combination results in an incredibly low density, making WASP-193b one of the least dense planets ever observed. In simple terms, it is a giant world that is mostly empty space. Planets like WASP-193b are often referred to as puffy planets or super puffs. Their atmospheres are so extended and diffuse that they can stretch far out from the planet's core, creating a swollen, cloud-like appearance. If it were possible to see WASP-193b up close, it would not resemble a solid sphere, but rather a soft, hazy globe with no clearly defined surface. The low density of WASP-193b presents a challenge to existing models of planetary formation. According to current theories, planets of this size should have accumulated far more mass during their formation. The fact that WASP-193b did not suggest that unusual processes may have shaped its evolution. One possible explanation is that the planet formed in a region of the protoplanetary disk with limited material, preventing it from gaining significant mass. Another possibility is that intense radiation from its host star caused the planet's atmosphere to expand and become less tightly bound over time. Stellar heating can cause gases to inflate, especially in planets that orbit relatively close to their stars. WASP-193b completes an orbit around its star in just a few days, placing it much closer to its star than Earth is to the Sun. This proximity exposes the planet to high levels of radiation, which likely plays a role in maintaining its inflated atmosphere. The heat from the star may cause the gases in the upper atmosphere to expand outward, further reducing the planet's overall density. The planet was discovered using the transit method, where astronomers detected periodic dips in the brightness of its host star. Because WASP-193b is so large relative to its mass, it blocks a significant amount of starlight during transit, making it easier to detect despite its unusual composition. Follow-up observations have been critical in determining its mass and confirming its low density. By measuring the gravitational effect the planet has on its star, scientists were able to estimate its mass and compare it to its size. The results confirmed that WASP-193b is far less dense than expected for a planet of its scale. The structure of WASP-193b is still not fully understood. It likely has a small, dense core surrounded by a vast envelope of hydrogen and helium gas. This outer layer may extend tens of thousands of kilometers into space, gradually thinning as it merges with the surrounding environment. Because of its extended atmosphere, WASP-193b is an excellent candidate for atmospheric studies. When the planet passes in front of its star, some of the starlight filters through its atmosphere. By analyzing this light, scientists can identify the chemical composition of the gases present, providing insights into its formation and evolution. Despite its size, WASP 193b is not a place where life as we know it could exist. It lacks a solid surface, and the conditions within its atmosphere are likely extreme, with high temperatures and pressures. However, its importance lies not in its habitability, but in what it reveals about the diversity of planetary systems. WASP 193b challenges the assumption that planets follow a predictable pattern of size and density. It shows that planetary systems can produce worlds that are far less compact and far more diffuse than previously thought. In the broader context of exoplanet research, discoveries like WASP 193b expand the range of known planetary types and force scientists to reconsider how planets form and evolve. Each unusual world adds complexity to our understanding of the universe. WASP 193b remains a distant and enigmatic object, a massive planet with surprisingly little substance, orbiting quietly around its star. Its existence serves as a reminder that not all planets are dense, solid worlds. Some are vast, light, and diffuse, shaped by processes that we are only beginning to understand. 55. Cancri is one of the most extreme exoplanets discovered to date, located approximately 41 light-years from Earth in the constellation Cancer. It orbits a Sun-like star and is part of a multi-planet system, making it an important target for studying how planetary systems can vary beyond our own. The planet is classified as a super-Earth, with a radius about twice that of Earth and a mass roughly 8 times greater. This suggests a dense, rocky composition, but the conditions on its surface are vastly different from anything found on our planet. One of the most striking features of 55 Cancri e is its orbit. It circles its star in less than 18 hours, placing it extremely close, about 25 times closer than Mercury is to the Sun. At this distance, the planet is subjected to intense stellar radiation and gravitational forces. Because of this close orbit, 55 Cancri e is likely tidally locked. This means that one side of the planet constantly faces the star, while the other remains in perpetual darkness. As a result, there is a dramatic temperature difference between the two hemispheres. The side facing the star experiences temperatures that can exceed 2,000 degrees Celsius, hot enough to melt rock. Under these conditions, scientists believe the surface may be covered in vast mahars of molten lava. These lava oceans could flow slowly across the surface, driven by temperature gradients and geological activity. On the opposite side, the temperatures are significantly lower, though still extremely hot by Earth standards. The transition between the two sides may involve powerful winds as heat is redistributed through whatever atmosphere the planet may have. The composition of 55 Cancri e has been the subject of ongoing study and debate. Early models suggested the possibility of a carbon-rich interior, leading to speculation that the planet could contain large amounts of diamond. However, more recent data indicates that it is more likely composed of silicate rocks, similar to Earth, but under far more extreme conditions. Observations from space telescopes have also revealed evidence of a dynamic atmosphere. Measurements of infrared light suggest that the planet may have a thin atmosphere composed of vaporized rock, including elements such as sodium, silicon, and oxygen. This type of atmosphere would not be stable over long periods and may be constantly replenished by volcanic activity and the evaporation of surface materials. The planet was discovered using both the radial velocity method and the transit method, allowing scientists to determine its mass, size, and orbital characteristics with a high degree of precision. Because it is relatively close to Earth, it has been one of the most extensively studied super-Earths. 55 Cancri E provides a valuable example of how planetary environments can differ dramatically depending on their distance from their host star. While it shares some structural similarities with Earth, its proximity to its star transforms it into a world of extreme heat and geological activity. The study of this planet also helps scientists understand the limits of planetary stability. Conditions on 55 Cancri E push the boundaries of what a rocky planet can endure, offering insights into how materials behave under intense harara and pressure. Although it is not a candidate for habitability, 55 Cancri E plays an important role in expanding our understanding of planetary diversity. It demonstrates that Earth-sized and super-Earth planets can exist in a wide range of environments, from temperate zones to extreme, high-temperature regions. As research continues, scientists hope to refine their models of the planet's atmosphere, surface composition, and internal structure. Future observations may reveal more about how lava worlds form and evolve over time. For now, 55 Cancri E remains a striking example of an extreme exoplanet, a dense, rocky world shaped by intense heat locked in a rapid orbit around its star and defined by conditions that challenge our understanding of planetary science. LHS 475b is a small, rocky exoplanet located approximately 41 light-years away from Earth in the constellation Octans. It orbits a red dwarf star and is notable for being one of the first Earth-sized planets confirmed using observations from the James Webb Space Telescope. In terms of size, LHS 475b is remarkably similar to Earth. Its radius is nearly identical, suggesting a comparable overall structure and composition. This places it firmly in the category of terrestrial planets, meaning it is likely composed of rock and metal rather than gas. The planet orbits very close to its host star, completing a full orbit in just 2 Earth days. This short orbital period indicates that it is much closer to its star than Earth is to the Sun. As a result, it receives a significantly higher level of stellar radiation. Despite its Earth-like size, the environmental conditions on LHS 475b are expected to be very different. Its proximity to a red dwarf star means it is likely tidally locked, with one side constantly facing the star, while the other remains in darkness. This would create a strong temperature contrast between the two hemispheres. One of the most important findings about LHS 475b is related to its atmosphere, or lack of one. Observations from the James Webb Space Telescope have shown no clear evidence of a thick atmosphere. This suggests that the planet may either have a very thin atmosphere or none at all. The absence of a substantial atmosphere has significant implications. Without an atmosphere to distribute heat, the side facing the star would become extremely hot, while the far side would remain much cooler. In addition, the surface would be exposed to stellar radiation, which could further limit the stability of any gases that might otherwise accumulate. However, scientists have not completely ruled out the possibility of a very thin atmosphere composed of heavier molecules such as carbon dioxide. Such an atmosphere would be more difficult to detect and could still exist under certain conditions. Further observations will be needed to confirm this. LHS 475b was detected using the transit method, where astronomers observed periodic dips in the brightness of its host star. The precision of the James Webb Space Telescope allowed scientists to confirm the planet's size and refine measurements of its orbital characteristics with a high level of accuracy. The importance of LHS 475b lies not in its habitability, but in its similarity to Earth and its accessibility for study. Because it is relatively close and orbits a small, dim star, it provides an ideal opportunity to test new observational techniques and improve our understanding of Earth-sized exoplanets. It also highlights the role of advanced telescopes in modern astronomy. The James Webb Space Telescope is capable of analyzing the light from distant stars and planets with unprecedented sensitivity, allowing scientists to detect subtle features that were previously beyond reach. By studying planets like LHS 475b, researchers can begin to build a clearer picture of how common Earth-sized planets are in the galaxy and how their atmospheres evolve over time. This, in turn, helps refine the search for planets that may have conditions suitable for life. LHS 475b represents a type of world that may be more common than previously thought. Small, rocky planets orbiting close to red dwarf stars, often with little or no atmosphere. While these environments may be harsh, they provide valuable data about the range of planetary conditions that exist. As observations continue, LHS 475b may reveal more about its surface, its potential atmosphere, and its interaction with its host star. For now, it remains a quiet, Earth-sized world, orbiting rapidly around a dim star, offering insight into one of the most common types of planets in our galaxy. TOI 700e is an Earth-sized exoplanet located approximately 100 light-years away from Earth in the constellation Dorado. It is part of the TOI 700 system, a planetary system that has become an important focus in the study of potentially habitable worlds. The system itself orbits a small red dwarf star, significantly cooler and less luminous than our Sun. This type of star is common throughout the galaxy, and many of the planets discovered in recent years have been found orbiting stars like it. Because red dwarfs emit less energy, their habitable zones are located much closer to the star. TOI 700e is particularly significant because it lies within this habitable zone. It is the fourth known planet in the system, joining others such as TOI 700d, which is also considered a potentially habitable world. The presence of multiple Earth-sized planets in the same habitable zone makes this system especially valuable for comparative study. In terms of size, TOI 700e is very similar to Earth, with a radius estimated to be just slightly smaller. This suggests that it is likely a rocky planet with a solid surface, rather than a gas-rich world. Its composition is expected to be similar to terrestrial planets found in our own solar system. The planet completes an orbit around its star in approximately 28 days. Due to its close proximity to the red dwarf, it is likely tidally locked, meaning one side of the planet constantly faces the star, while the other remains in darkness. This could result in a stable temperature gradient between the two sides, depending on the presence and composition of its atmosphere. One of the key unknowns surrounding TOI 700e is whether it has retained an atmosphere. A sufficiently thick atmosphere could redistribute heat across the planet, reducing temperature extremes and potentially allowing for more stable surface conditions. Without an atmosphere, the planet would experience more extreme contrasts between its day and night sides. The discovery of TOI 700e was made using data from NASA's Transiting Exoplanet Survey Satellite, or TESS. The transit method allowed scientists to detect the planet as it passed in front of its host star, causing a measurable dip in brightness. Subsequent analysis confirmed its size, orbit, and position within the habitable zone. The TOI 700 system has become a key target for further observation, particularly with advanced instruments such as the James Webb Space Telescope. Because the star is relatively close and dim, it provides favorable conditions for studying the atmospheres of its planets, if they are present. One of the advantages of studying a system like TOI 700 is the ability to compare multiple planets under similar conditions. By examining how planets such as TOI 700 and TOI 700T differ in size, orbit, and potential atmosphere, scientists can gain insights into how small changes in planetary characteristics can lead to very different outcomes. TOI 700T is considered one of the more promising Earth-sized planets discovered in recent years, not because it is known to be habitable, but because it offers the right combination of size, location, and observational accessibility. It represents a type of planet that may be common throughout the galaxy, but has only recently become detectable with modern instruments. The study of planets like TOI 700e contributes to a broader effort to understand how frequently Earth-like conditions might arise. It helps refine models of atmospheric retention, climate stability, and planetary evolution in systems dominated by red dwarf stars. While many uncertainties remain, TOI 700e stands out as a compelling example of a temperate, Earth-sized world beyond our solar system. Its position within a multi-planet habitable zone system makes it especially valuable for ongoing research. As future observations provide more data, scientists hope to determine whether TOI 700e possesses an atmosphere, and if so, what its composition might be. These answers will help place the planet within the wider context of potentially habitable environments in the galaxy. For now, TOI 700e remains a quiet, distant world, orbiting steadily within the habitable zone of its star. One of the many planets that continue to shape our understanding of what is possible beyond Earth. Over the past few decades, the discovery of exoplanets has transformed our understanding of the universe. What was once considered uncertain, the existence of planets beyond our solar system, is now one of the most active and rapidly advancing areas of modern astronomy. As of today, thousands of exoplanets have been confirmed, with many more candidates awaiting verification. These planets vary widely in size, composition, and environment, ranging from small rocky worlds to massive gas giants, from temperate zones to extreme, high-temperature orbits. The planets explored in this series, from Gliese 12b to TOI 700e, represent only a small fraction of what has been discovered. Each one offers a different perspective on how planetary systems form and evolve, and together they reveal a level of diversity that challenges earlier assumptions about what a typical planet might look like. One of the key developments driving this progress has been the advancement of detection methods. The transit method, which measures dips in a star's brightness, has been responsible for identifying a large number of exoplanets. The radial velocity method, which detects the gravitational influence of a planet on its host star, has also played a crucial role in confirming their existence and measuring their mass. More recently, space-based observatories such as the Kepler Space Telescope, the Transiting Exoplanet Survey Satellite, TESS, and the James Webb Space Telescope have significantly increased both the quantity and quality of available data. These instruments allow scientists not only to detect planets, but also to begin analyzing their atmospheres and chemical compositions. One of the central goals of exoplanet research is to identify planets that may have conditions suitable for life. This typically involves focusing on Earth-sized or slightly larger rocky planets located within the habitable zones of their stars. However, as discoveries continue, it has become clear that habitability may not be limited to Earth-like conditions alone. Planets such as K218b suggest that entirely different types of environments, including ocean worlds with thick hydrogen atmospheres, could potentially support life under the right circumstances. At the same time, extreme planets like 55 Cancri demonstrate the wide range of conditions that can exist, even among rocky worlds. Another important area of research involves understanding how planetary atmospheres form, evolve, and in some cases, disappear. Factors such as stellar radiation, planetary gravity, and magnetic fields all play a role in determining whether a planet can retain an atmosphere over long periods of time. The study of multi-planet systems, such as TOI 700, has also provided valuable insights. By observing several planets within the same system, scientists can compare how differences in size, distance from the star, and atmospheric composition influence their development. This comparative approach helps refine models of planetary formation and climate behavior. As detection methods continue to improve, the focus is gradually shifting from discovery to characterization. Rather than simply identifying new planets, scientists are increasingly interested in understanding their detailed properties, including surface conditions, atmospheric chemistry, and potential signs of biological activity. Future missions and telescopes are expected to expand this capability even further. Planned observatories will aim to directly image exoplanets, analyze their atmospheres with greater precision, and search for biosignatures, chemical indicators that could suggest the presence of life. Despite these advancements, much of the universe remains unexplored. The vast distances between stars mean that even the closest exoplanets are far beyond the reach of current spacecraft. For now, our understanding of these worlds depends entirely on indirect observation and careful analysis of light. What has become clear, however, is that planets are not rare. They are a common feature of the galaxy, forming around stars of many different types. The Milky Way alone is estimated to contain hundreds of billions of planets, many of which remain undetected. This realization represents a fundamental shift in perspective.